Hi there, welcome to this PowerPoint video lesson on the graphical transformations of functions. Okay, so first off, we have these 8 different transformations. I would like us to think about them as 4 pairs. So 1 and 2, these are translations or shifts in either the y direction or in the x direction. Transformation 3 and transformation number 4, these are either stretches or compressions. Transformation 5 and 6, these are reflections either across or in the x-axis or reflection across the y-axis. There's a little bit more that goes on with the modulus transformations, number 7, number 8, and we'll look at each of these later on. Also, I think it's important for us to think about the transformations in 2 groups. So the ones on the left, where the transformation operates on the outside of the function, these change the y values. Instead, the ones on the right, where the transformation is applied inside the function, inside the brackets of the f of x, here the x values change. Okay, so specific examples. So first one, where we have f of x with plus c outside the function, this is shifting up by c units. So if we start with our basic quadratic, effectively y equals x squared, we apply plus 2 outside the function, then this translates the curve up by 2 units. Similarly, if we apply f of x minus 4, subtract 4 outside of the function, this is going to shift our function or curve down by 4 units. So in this case, we have f of x or y equal to 2x, a straight line with gradient 2 going through the origin. This is shifted down by 4 units. So translation vector of 0 minus 4. Transformation number 2, so where we have f of x plus c inside the function, this is going to shift everything by c units to the left. So I've chosen a very specific cubic where we have roots when x is equal to 2 and when x is equal to 0. This gives us our 2 x-intercepts where the curve crosses the x-axis at 2, 0 and at 0, 0. So when we apply the function f of x plus 2, everything is being shifted by 2 units to the left, or we have a translation vector of minus 2, 0. We can check through this very carefully with our algebra because we can replace everywhere we've had x in the original function by x plus 2, and if we did that, we would find that our new cubic would be x squared multiplied by x plus 2 in brackets. So that shows that the x-intercepts will now be at 0, 0 and minus 2, 0. Specifically, it's the x-intercept that was previously at 2, 0. This gets shifted to the new x-intercept at 0, 0, and the previous x-intercept at 0, 0. This has been shifted now to minus 2, 0, again 2 to the left. Okay, be very careful with transformation number 2 in that we don't want to think about this as a horizontal shift in the positive x direction. We're not shifting to the right. Transformation where we have k f of x or k multiplied by f of x. Here, the graph is going to be stretched by a factor of k in the y direction. So in this example, we're starting with the original function sketched out in red, f of x being just the quadratic x squared. If we apply the transformation 2 times f of x, then all of the y values are going to be stretched by a factor of 2 in the y direction. So if we look at a few specific points, the origin 0, 0, that stays at 0, 0. It's the only invariant point, where we previously had the coordinates 1, 1 and minus 1, 1 on the red graph. these are going to be stretched to the points 1, 2 and minus 1, 2. And again, the pairs of points at 2, 4 and minus 2, 4, these are going to be stretched up to 2, 8 and minus 2, 8. So it's always the y values that are effectively doubling. The coordinates at 3, 9 and minus 3, 9 get stretched up to 3, 18 and minus 3, 18 on the new blue graph g of x. And also the points 4, 16 and minus 4, 16 will get stretched up to the points 4, 32 and minus 4, 32. We look at transformation number 4. Here we have f of kx with kx inside of the function. This is effectively a compression by a factor of 2 inside the function when we apply f of 2x. So a compression by a factor of k, or specifically a factor of 2 in this example, where the quadratic y or f of x equal to x squared, it's being compressed by a factor of 2 in the x direction. And if we check with our algebra, actually if we apply 2x and replace everywhere we had x before with 2x, actually this new function, which I've called h of x, is actually equivalent to 4x squared. So if we look at a couple of pairs of points, where we had the points 4, 16 and minus 4, 16, these are going to be compressed in, so the x values are actually go from 4 and minus 4 to 2 and minus 2, the same y value at 16. And also if we look at the pairs of points at 2, 4 or minus 2, 4 on the original function f of x, these get compressed in to 1, 4 and minus 1, 4. So it's the x values that get halved or compressed by a factor of 2, the same y values. If we were to make a comparison between these two transformations, k of f of x and f of kx, we do need to be careful because they're not doing the same thing. K of f of x is stretching by a factor of k in the y direction. F of kx is actually compressing by a factor of k in the x direction. So it's definitely worth looking at a couple of pairs of examples like the one I've given here. So starting with the quadratic x squared for f of x, 2 times f of x is giving us 2x squared. If we have f of 2x in this example, actually it's 2x in brackets all squared, which is actually equivalent to 4x squared. Okay, if we were to revisit transformation number 3, this time with a scale factor k outside the function, which is less than 1. So we said that k multiplied by f of x is a stretch by a factor of k in the y direction. Here, if we have half times f of x, it's going to be a vertical stretch in the y direction by a factor of a half. Okay, so again, we're starting from the function, the graph sketched out in red, f of x here is equal to x plus 1 in brackets, all cubed, plus 1. So this is actually the cubic where if we started from just y equals x cubed, we're just shifting that cubic by 1 to the left and 1 up. So we can use that to connect with our transformations. Number 1 and transformation number 2, the translations or shifts. And if we look at this new cubic, so it's going from x plus 1 in brackets or q plus 1, our red curve, and it's being stretched by a factor of half in the y direction. So again, looking at some specific points, where we had the point at 110, that point is going to be stretched by a factor of half to the point 15. So it's the y value that's being halved. Next point along where we had 0, 2 as the previous y-intercept, the y value again gets halved, so it now goes to the point 0, 1. Our next point along where we have minus 1, 1 on the original f of x function, the y value again is halved to give us minus 1 half. Also, if we go to the point minus 3, minus 7, the y value gets halved to minus 3.5, or the half of minus 7. And one final point to pay attention to, our invariant point, is where we have the x-intercept at minus 2, 0, because that's the only y value when y is 0. It doesn't matter what we multiply 0 by, it stays as 0. So it's only the x-intercept that will be the invariant point subject to this transformation. Transformation number 5, here is going to be a reflection. So the minus of f of x, the minus on the outside of the function, it tells us that all of the y values are going to be reversed. So in this quartic, a very specific quartic with roots at when x is equal to 2 and also when x is equal to 0. So we have x-intercepts at 2, 0 and 0, 0. After this transformation, the roots are still where they are, the x-intercepts don't change, but all of the y values get reflected. So the positive y values now become the same corresponding magnitude y values, which are now negative in sign. So it's a reflection in or across the x-axis. Now we can check it algebraically because it allows us to see the first quartic, f of x. It's a quartic with a positive coefficient to the x to the power 4, which means we're going to have a w kind of shape. If we have a negative coefficient to the x to the power 4 term in the quartic, we're going to have an m kind of shape. Transformation number 6, using the same quartic, but if we have now f of minus x inside the function, this is going to be a reflection across the y-axis. Okay, so we replace the x in the original function f of x with minus x. So we can see that the roots, and we can check this algebraically, where we had the x-intercepts at 2, 0 and 0, 0. These actually get reflected across. So the root at 0, 0 stays where it's at, but the root at 2, 0 gets reflected across the y-axis to minus 2, 0. We can think about that or understand it in terms of where x was before. We're actually replacing it with the negative of that x value. So where we had x as 2 before, we now have to replace it with minus 2, and that gives us the same y value as before. Transformation number 7, so where we have the modulus outside of the function f of x. All of the positive y values stay exactly as where they were before, and the negative y values get reflected across the x-axis. So to just check, for example, where we had x as 3 before, f of 3 was negative 0.5. If we take the modulus of negative 0.5, it goes up to 0.5, and when x was 4, f of 4 was minus 1, and if we take the modulus of minus 1, it also reflects across the x-axis to 4, 1. And finally, our last transformation, transformation number 8. Here we have f of the mod of x, or the modulus of x inside the function. Okay, so now where x values are either 0 or positive, nothing's going to change with the mod of x. So what we need to pay attention to is where the x values are negative. And when the x values are negative, we ignore the previous part of the graph where the x values were negative. And what we actually need to do is we need to reflect the positive x values, or the part of graph, the part of the original graph where the x values were positive. We need to reflect that part across the y-axis. So to check why we kind of need to do that with a couple of pairs of exact values, when x was minus 1 before, we put minus 1 into the modulus function, or actually the new part on the graph should correspond to the point f of 1. And similarly, where -2 is being put into the modulus function, or the new point on our transformed graph should correspond to f of 2, and so on. Thank you for watching.